There's a camera that we're building called Scuba 2, replaces Scuba 1. Our opponents, our competitors next door, over here in this little telescope, that's Caltech. They built a camera to compete with our Scuba, and they said they were going to build a camera that was going to eat ours alive. They called it Shark. Which has a similar, submillimeter something, common, user kilometer rate, submillimeter. I can't remember the rest of it. And Waterloo and ATC are the principal investigators. We're joint partners in building this camera, and then these are our Canadian partners, and this is their UK partners, and there's the telescope itself. And this instrument is just about finished. We were going to actually start science observations yesterday, but the cryostat that keeps the instrument cold at 60 millikelvin, 60,000th degree above absolute zero, got a blockage and started warming up yesterday. So it'll be another week before we actually start science. And I got a whole bunch of details here about the details of using this camera. This is the detectors on it. I'm just going to say the only thing that's really important is it observes 450 and 850 microns. Just short of a millimeter. It's just into the submillimeter. Shorter than 450 microns, you really can't do from the site. It's just not good enough. But just the camera. Here's our camera arriving. This is our camera box. Cameras in this box. Here we unpack it. There's the camera. It's not the electronics for the camera. It's just the optical part. This is the cryostat. Everything in here is at liquid helium temperatures, and then we lift it up into the observatory with the crane, and we drop it onto this platform, which is left later on. We lift it up, and I always say everybody's bowing in front of it. We finally arrived. They're actually inspecting it. And I have lots more pictures of it I just took when I was there recently when it was all mounted in the telescope. And just to say that here's our old camera, which was the best. When we decommissioned this 2 years ago, Scuba was the best camera in the world by far. Here's Orion, which is a very bright object in the winter sky here. That's a 10-hour picture of Orion. This was 24 minutes with Scuba 2 with only 1/4 of the detectors working. And so it's just an enormous improvement. And it's huge. This camera's about 1,000 times faster than Scuba, which was the biggest camera in the world, on the best telescope, biggest telescope in the world. So we're all really eagerly waiting, like any time now next week. Actually, February 10th, actually. We'll start science observations. What can you do better? You can go higher. And so there is this desert in Chile at 5,000 meters here where we're planning on putting a telescope. But we're actually building this. This is funded. It's about $1 billion telescope. And it makes use of a principle called interferometry, which is that you can simulate a large antenna by taking smaller telescopes and connecting them electronically. And here's the plan. You add a camera large millimeter array. Again, it's barely submillimeter. It will work at 450. You even work at 350 microns, but not that well. But it's pretty good. It's got 64 of these antennas, and they're quite large. You can see people here. A little bit smaller than the JCMT that I showed you before. But that's the next stage. This is what everybody's waiting for. This is a multi-billion-dollar project. The World Observatory, every astronomer, every organization around the world is involved with it. And these are actually movable antennas. Here's an artist's picture of what it's going to look like, but they can be moved out to here. Moving them further apart gives you better resolution. And I'm trying to build this. We're the lead institution. Well, Cornell is 20%, Caltech's 20%. Waterloo is leading Canadian consortium, which no longer just includes UBC. We've got 4 other universities unofficially in it to build this just above that previous site. And this will be the largest submillimeter telescope in the world, and we're hoping to be in operation in 2016. And you just about can't do better. And it still only goes down to about 3. Oh, this one will actually work to 200 microns. There's a little window by going an extra 600 meters higher. We can get down to 200 microns some of the time, maybe 10% of the time. But if you want to do any more than this, you have to go to space. Except for these narrow windows at 200 microns, 350, 450, and at 850 microns, which are not all that transparent, you have to go into space. So what have we done in the past? Well, here's a whole long listing going back to IRAS in 1983. This was the first space mission that I was a guest investigator. This is a NASA project. I was the first guest investigator in that program with NASA when I was a professor at the University of Washington. Great satellite. I have a graduate student who's doing her PhD thesis based, the first half of it's based on IRAS data that's never been processed before, and so that's great. And then there's a bunch of other missions. I worked a lot on this one, for example. ISO was an all-sky survey. I'm sorry, it wasn't an all-sky survey. This was an all-sky survey. This was a very, much more sensitive. Then there was a couple of other missions that were very much tuned to do spectroscopy. For example, this Waterloo I mentioned before. And then there was the Canadian, Swedish, Canadian, French satellite we launched from Siberia in the middle of the winter. I'll show you the launch. I got a little movie of this. We launched this with a 2 to 3 year lifetime in 2001. It's still operating today. What's great about this, I've been involved now, since then I've been involved in a couple of other missions, and the amount of stuff you have to do, the bunch of paperwork you have to do, the space qualification of every part you put into it is just incredible. We built this with Radio Shack components. Not even just, you know, industrial grade or commercial grade. This was just we went and ordered things out of catalogs and just built the satellite. And it had 5 receivers, 2 of which failed on launch, 1 of which we recovered a couple months later. The last one works, but it's hard. They can't fix the tuning on it. And in particular for this line, 119 gigahertz, which was my main science goal. This was to study this. But we've managed to get some science out of it. So this was an astronomy mission and an ozone chemistry mission half-time. The ozone chemistry is going on, but I've now got another satellite that I'm using. We turned off the astronomy because we have a better satellite that I'll tell you about in a few minutes. Here's how you fold up the solar panels. We were just folding this up in Siberia, assembling this in the Russian launch place. Here's our last view we ever saw. It's all folded up going into the rocket. Last time we ever saw the satellite, never see it again. Here's it out on the rocket. I don't know if you recognize these. This is a Start 1 launcher. These are made for nuclear bombs. You know, these are supposed to launch them from this place in Siberia. Washington, we actually did launch from this place, and we went right over Washington, over the North Pole, and right over Washington, but it stayed up. These are meant to be quick launch things, you know, short lead time, and dispersed because they got wheels on them. So I'll show you. They were so matter of fact about launching this, the Russians, that they told us a year in advance when they were going to launch, and they were only off by about 15 seconds. We wanted NASA to launch it. NASA really wanted to launch it. They wanted to charge us twice as much to launch on a mission, on a rocket that had never had a successful launch, had never had a failure, and it had many, many, many launches. And NASA, of course, is infamous for never launching on time. So we went with the cheaper Russian one and took it to Siberia. And so they were so matter of fact because they didn't want to even take video of it. So one of our guys had a 1 megapixel camera which he degraded the resolution so he'd have enough memory. This is 2001 and cameras were not that big. And he took a handheld video of the launch, and I'll show you the launch. So this is real time, you know, launching. Could have been a nuclear bomb, but this is us. And there's drops off the nose cone on the carrier tube, so this is real time, right? This is not, you know, wait around, countdown for 10 hours checking dials and things like this. And it goes up like this. It's very matter of fact, they just drove it out into a field. They towed it out into a field and parked it. And it's just sitting there, and then they said it's time for the launch. They push the button, and it goes up like that. And then there's a puff of smoke off to the left in a moment. There it goes, puff of smoke. And it's pushed out by compressed air as the engines have ignited, and there it's gone. So I do real rocket science. We build rocket things. Not that touch the fuel part, but the top part of the top of mine. Actually, that's our satellite. I did the first tests of our instruments in the lab. I went over to Sweden for a week and got to play with it. And that was the last one I ever saw because I wasn't there for launch. I didn't want to go to Siberia in the middle of February, and I got a whole bunch more pictures of this, and they all seem to include vodka. I don't know. This is high-tech science. Well, it's all Radio Shack. It's high-tech science, and every picture has vodka in it, except for the actual launch day. Well, the end of the launch. After this, there's lots of vodka too. Some of the pictures of the skies camera. NASA had a mission that's relevant to this. Spitzer, which just ran out of helium last year, and so it's warmed up again. But it's the latest far-infrared camera, and it's also a mid. This is near and mid-infrared, but it did have some